Nothingness, the absolute void, is a concept that confounds the human mind. We tend to believe that, for anything to exist, it must have originated from something. So, how did everything begin? We often claim it started from nothing, but how can nothing transform into something? In the vast cosmic expanse, where galaxies glow and black holes consume matter, the concept of nothingness challenges our understanding of the universe. This is not just a philosophical idea. It is a cornerstone of cosmology that has intrigued scientists and thinkers for centuries. Picture a region of space devoid of stars, planets, or any matter, just pure emptiness. It resembles a quiet corner of the universe where conventional physics may not apply. The idea of nothingness seems contradictory, yet it is crucial in the study of cosmology and science. To understand the mysteries of the universe, one must first grasp what nothing means in the context of space. The emptiness of space might seem like a perfect vacuum, completely devoid of matter or energy. While this simplistic view holds some truth, it does not capture the complexity revealed by scientific discoveries. In modern cosmology, nothingness is not an absolute void, but a complex and dynamic terrain that defies our preconceived notions. Let us explore this concept through the scientific lens. Contrary to what one might think, the vacuum of space is not truly empty. It is filled with quantum fluctuations, where particles and antiparticles spontaneously appear and annihilate each other. These fluctuations give the vacuum a dynamic and ever-changing nature. Space is intrinsically linked to the fabric of space-time, as described by Einstein's theory of general relativity. Even in areas without visible mass, massive objects can warp space-time, influencing the paths of nearby objects. When we look into space, we can detect the faint echo of the Big Bang, the cosmic microwave background radiation, a relic of the early universe that reminds us space has evolved over time. Despite our advances, the concept of nothingness in space remains a profound puzzle for scientists and philosophers. There are theories suggesting the existence of regions in the universe where matter density approaches near absolute nothingness. Though these ideas remain speculative, some hypothesize that there could be areas in the cosmos with extremely low matter density, verging on voids. If such regions exist, they might provide essential insights into the nature of space itself. Is empty space truly devoid of all matter and energy? This seemingly simple question opens a Pandora's box of scientific and philosophical exploration. Traditionally, space is seen as a pristine vacuum, a barren canvas without matter or energy. This notion fits our understanding of emptiness, but as we delve deeper into cosmology, we find that reality is far more complex and intriguing than we ever imagined. In the realm of quantum mechanics, which governs the behavior of particles on the smallest scales, we encounter a concept that challenges our idea of nothingness: quantum fluctuations. These fluctuations suggest that, even in the emptiest parts of space, particles and antiparticles can spontaneously appear, interact briefly, and then annihilate each other. These fleeting events defy our conventional understanding of emptiness, bringing a dynamic quality to the void. Additionally, Einstein's theory of general relativity teaches us that space and time are part of a four-dimensional fabric called space-time. Massive objects, such as planets, stars, and black holes, can warp this fabric, affecting the motion of nearby objects. Thus, the idea of a completely empty, unaltered space becomes an elusive dream. How does nothing relate to the presence of dark matter? And what does it reveal about the universe's intricate structure? To solve this cosmic puzzle, we must first understand dark matter itself. Unlike ordinary matter that forms stars, planets, and galaxies, dark matter is invisible to our senses and reveals its presence only through the gravitational forces it exerts. It represents the ultimate form of nothingness, eluding direct observation and defying traditional definitions of matter. Dark matter's existence was inferred through the observation of galaxies and their movements, as the gravitational pull of visible matter alone couldn't account for their behavior. To explain this discrepancy, scientists propose the existence of an unseen, intangible substance, dark matter. that fills cosmic voids and holds galaxies together. The Big Bang Theory suggests that the universe began as a singularity, a point of infinite density and temperature about 13.8 billion years ago. This moment of cosmic inception marked the birth of space and time itself, from what might be considered nothing in conventional terms. But how does this theory, describing the explosive birth of our universe, relate to the concept of nothing? To understand this, we must grasp the nature of the singularity at the Big Bang's moment. The singularity represents a state where the laws of physics break down, a point of infinite density and zero volume, defying our usual understanding of matter and space. In this sense, the singularity can be seen as a manifestation of nothingness, a point where the universe lacked its familiar structure and dimensions. However, this apparent nothing was filled with potential. As the universe expanded from the singularity, it underwent rapid inflation, causing space to stretch exponentially. In an instant, the universe transformed from a state of cosmic nothingness into a cauldron of energy, particles, and fundamental forces that shape our reality. During the initial moments of the Big Bang, the universe was extremely hot and dense, resembling a primordial soup of particles and radiation. In a fraction of a second, it underwent a series of transformations, including nucleosynthesis, where the first atomic nuclei formed. This cosmic evolution led to the emergence of stars, galaxies, and the intricate structure of the cosmos we observe today. How do we know the Big Bang happened? There's a lot of evidence supporting the Big Bang theory. One key piece is the cosmic microwave background radiation, which is like the afterglow from the early universe. This radiation gives us a picture of the universe just 380,000 years after the Big Bang, before which the universe was too hot and dense to take pictures of. Arno Penzias and Robert Wilson discovered this radiation by accident in 1965. The CMB's uniformity and slight fluctuations support the idea of cosmic inflation and rapid expansion of the universe. Another piece of evidence is the redshift of galaxies, meaning galaxies are moving away from us, showing the universe is expanding. Edwin Hubble first observed this in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us, supporting the idea that the universe was once much smaller, hotter, and denser. However, the Big Bang theory raises some big questions. For example, it doesn't explain what happened before the Big Bang or what lies beyond the part of the universe we can see. It also introduces the idea of cosmic inflation, a rapid expansion that happened right after the Big Bang. Before the discovery of the cosmic microwave background radiation, there was a popular idea called the steady-state theory. This theory suggested that the universe has no beginning or end but stays the same overall, even though it's expanding by constantly creating new matter. This theory was popular in the 1940s but lost support when scientists discovered the CMB radiation in 1965, strongly supporting the Big Bang theory. Additionally, there are theories like the cyclic model, which suggests the universe undergoes endless cycles of expansion and shrinking. After the Big Bang, the universe expanded and cooled. In the beginning, it was a hot, dense soup of particles. As it expanded, it cooled down, allowing particles to come together and form the first atoms. These atoms then formed the first stars and galaxies. The universe's expansion continues today, with galaxies moving away from us in all directions. Going even further back, the first long-lived particles were protons and neutrons, which make up the atomic nucleus. These appeared around 1,000th of a second after the Big Bang. Before that, there was no material as we know it. But physics allows us to trace the timeline even further back to processes that happened before any stable matter existed. To understand how the universe could begin from nothing, we need to explore the strange world of quantum mechanics. In quantum physics, nothing isn't the absence of anything, but rather a state of vacuum energy where particles constantly pop in and out of existence. This phenomenon is known as quantum fluctuations. Quantum fluctuations happen in what is called the quantum vacuum, a state with the lowest possible energy where particles can momentarily appear and then vanish. According to quantum mechanics, these fluctuations can lead to the creation of a universe. So, in this context, nothing is an energetic state that can give rise to matter and energy. A key concept here is Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be known precisely at the same time. This principle allows particles to temporarily pop into existence from the vacuum, as long as they disappear quickly enough to comply with the law of conservation of energy. Quantum fluctuations cause particles to appear and disappear shortly after. This might sound strange, but such particles have been observed in many experiments. The vacuum of space is filled with particles constantly being created and destroyed, seemingly out of nothing. This suggests that the quantum vacuum is actually something rather than nothing. Where did space-time itself come from? To answer this, we need to go back to the very beginning, into the Planck epoch. This period was so early in the universe's history that our best theories of physics no longer work. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time themselves were affected by quantum fluctuations. Usually, physicists use quantum mechanics for tiny particles and general relativity for large cosmic scales. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines the two. We don't have a perfect theory of quantum gravity yet, but there are ideas like string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time is the result of quantum processes, which are hard for us to understand because we are used to the large-scale world. Quantum fluctuations happen constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a short moment, and then destroy each other. This phenomenon is known as quantum foam. But quantum fluctuations alone don't explain the universe's vast scale and complexity. There is dark energy, a mysterious force that fills all of space and accelerates the expansion of the universe. While we don't fully understand dark energy, it's believed to play a crucial role in the creation and evolution of the cosmos. So, how do we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, setting the stage for the formation of galaxies, stars, and planets. In the Planck epoch, our usual understanding of space-time and cause and effect breaks down. Despite this, all candidate theories of quantum gravity describe something physical happening in the Planck epoch, some quantum precursor to ordinary space and time. But where did that come from? Even if causality doesn't work in the usual way, it might still be possible to explain parts of the Planck epoch universe in terms of other parts. Unfortunately, our best physics can't provide clear answers yet. Until we develop a theory of everything, we won't be able to give a definitive answer. The most we can say with confidence is that physics has not found any confirmed instances of something arising from nothing. In this context, the concept of nothingness takes on a dynamic and evolving character. It is not a stagnant void, but a canvas upon which the universe paints its story, a story that began with the explosive birth of the cosmos. The question of whether the vacuum of space truly constitutes emptiness, devoid of particles or fields, is a cornerstone of advanced cosmology. At first glance, we might envision the vacuum of space as an empty void, a vast expanse devoid of matter or energy. Yet, as we delve into the profound world of quantum mechanics, we encounter a remarkable revelation. The vacuum is not as vacant as our classical intuition suggests. Furthermore, the vacuum of space is not merely a passive backdrop, but an integral part of the cosmos. It hosts fields that govern the universe's fundamental forces, such as the electromagnetic field. These fields extend throughout space, even in regions perceived as empty. In advanced cosmology, it becomes evident that the vacuum of space is far from a true void. It is a dynamic arena where the boundary between nothing and something blurs, alive with the quantum fluctuations of particles and fields, challenging our preconceived notions of emptiness. Moreover, this concept has practical implications. Scientists harness the energy within these quantum fluctuations through a phenomenon known as the Casimir effect. When two parallel conducting plates are placed close together in a vacuum, they experience a minuscule but measurable attraction due to the suppression of certain vacuum fluctuations between them. This effect, though subtle, demonstrates the tangible consequences of nothingness within the vacuum. For interpretations of nothing, to truly answer the question of how something could arise from nothing, we first need to understand several interpretations of nothing. This is the state where the essential building blocks for everything we see are absent. Imagine a universe with no galaxies, stars, planets, or even humans. Everything we know and interact with is made up of tiny subatomic particles. These particles are the building blocks that shape our universe. If we start with a universe full of matter, we can understand how it grows, cools down, and is influenced by gravity to become the universe we see today. Stars go through life cycles, creating heavier elements that lead to the birth of new stars, planets, organic compounds, and eventually life. But here are some big scientific questions. How do we end up with a universe dominated by matter and not one with equal amounts of matter and antimatter? This is one of the biggest mysteries in physics. The universe is made almost entirely of matter, with hardly any antimatter. Every star, planet, and galaxy we've observed is made of matter. So, how do we get this surplus of matter? This puzzle is known as baryogenesis, the process of creating an excess of baryons over antibaryons in the early universe. Scientists have many theories, but we still don't have a definitive answer. We don't know why there's more matter than antimatter instead of a balance. Our second interpretation of nothing is the emptiness of vast space. Maybe you think of nothing as truly having no things at all. If that's the case, then the first explanation of nothing, with missing building blocks, doesn't quite fit because it still involves something. To really understand this concept of nothingness, let's imagine getting rid of every basic element of matter. That means removing every single particle and every bit of energy. If we could manage to remove all of these, what would remain? Just a vast expanse of empty space. No particles, no matter, no radiation at all. This is what some scientists see as the true scientific meaning of nothingness. Space-time itself, guided by the principles of general relativity, still exists. The speed of light and gravitational constants still retain their values. And most importantly, there's something called zero-point energy. Even in the emptiest space, there's still a tiny amount of energy. Today, we see this as dark energy, which is driving the expansion of the universe. But even in this extremely empty scenario, some fundamental aspects still remain. The laws of physics are still there. Quantum fields, like the electromagnetic field, the gravitational field, the Higgs field, and fields related to nuclear forces, still exist. So, even without any matter or radiation, this version of nothing still gives rise to an intriguing universe. It's fascinating to think that, even in the absence of everything we see, the universe can still be a dynamic and captivating place. The third interpretation of nothing, for scientists, is the idea of nothingness as the lowest energy state possible. Right now, our universe has something called zero-point energy. This is a tiny amount of energy that exists everywhere in space. We don't know if the zero-point energy is the absolute lowest energy possible, or if there's an even lower energy state we haven't discovered yet. There's a chance we might be in a false vacuum state, with the true vacuum, or the absolute lowest energy state, either near zero or perhaps even reaching or surpassing it. If the universe changes from this false vacuum to a true vacuum, it could trigger a catastrophic event called vacuum decay. This would drastically change the universe. Photons, which are particles of light, would get mass. The electromagnetic force would be confined to short distances, and most of the sunlight from the sun wouldn't reach Earth. Thinking of nothingness as the ultimate lowest energy state, means imagining a situation where all matter, energy, radiation, and any distortions in space-time are removed. What remains is a state of perfect emptiness, but with the laws of physics still in place. This ultimate low-energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space-time and the laws of physics would still exist. In this state, there would still be a backdrop for events to happen, but without any actors or actions. It would be like a play with no characters, storyline, or setting, just an empty stage. Imagine reaching the universe's true foundational state, whatever that might be. In this state, all matter, energy, and any distortions in space-time would be removed. What would be left is the ultimate material emptiness. This ultimate low-energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space-time and the laws of physics would still exist. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the framework of space-time and the laws of physics remain. It's another incredible mystery that keeps scientists exploring and searching for answers. This is the most extreme interpretation of nothing. It's the idea that true nothingness only happens when the entire universe and its governing laws are completely gone. This is a radical idea that goes beyond our usual understanding of reality. Imagine getting rid of everything, including space-time and even the laws of physics. This kind of nothing is beyond what we can define with physics, because it represents an absolute void, a total absence of everything. From a physics standpoint, this idea is challenging. How can something like space-time exist if there's no space or time? How can the laws of physics work if there's no framework for them? This kind of nothing is hard to comprehend and might not have any real-world meaning. Thinking about this ultimate nothingness brings up many questions without clear answers. For instance, how could space and time begin in a place where they don't exist? Is it possible to have something without space or something starting without time? Imagine an absolute nothingness, a complete void. From a physics perspective, it suggests a state beyond the limits of space and time, from which our universe and its laws might have originated. However, we're not sure if this idea is meaningful or just a product of our imagination. This concept raises many difficult questions. For instance, how can space and time begin in a place or moment where neither exists? Can we even imagine something existing outside the universe without space or starting without time? Where would the rules that govern particles and their interactions come from? This idea of nothingness, while it seems philosophically complete, might not have any real substance. It could just be a way for us to understand things that are beyond our reality. When scientists talk about nothing, they often assume everyone has the same idea of what nothing means, but that's not always the case. Different people in different contexts can change how we understand nothing. While theories about nothing are grounded in scientific principles and observations, the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provides insights into the early universe's conditions. Detailed measurements of the CMB have helped our understanding of the universe's age, composition, and structure. Observations of the expansion of the universe, as described by Hubble's law, support the idea that the universe began from a hot, dense state. Additionally, the discovery of dark matter and dark energy, which make up most of the universe's mass energy content, suggests that our understanding of the universe is still incomplete. The phrase, something from nothing, might mean creating something entirely new where there was truly nothing before, but not everyone agrees on what nothing really means. In the end, it's important to understand that, in simple terms, nothingness refers to the absence of matter, energy, and even the space-time fabric. However, the reality is far more intricate. Quantum mechanics suggests that, even in a perfect vacuum, particles and antiparticles constantly pop in and out of existence. This quantum fluctuation could be the key to understanding how our universe emerged from a state of nothingness. One essential player in this cosmic dance is dark matter, an elusive and mysterious form of matter that does not emit, absorb, or reflect light. making it invisible and detectable only through its gravitational effects. Dark matter, despite its elusive nature, consists of about 27% of the universe, playing a crucial role in its formation and evolution. Dark matter acts as the cosmic scaffold upon which the universe is built. It is believed that dark matter provided the necessary gravitational pull to bring together ordinary matter and form galaxies, stars, and planets. Without dark matter, the universe would be a vastly different place, likely devoid of the complex structures we observe today. The initial conditions of the universe, characterized by quantum fluctuations, allowed for the uneven distribution of dark matter. These fluctuations grew over time, creating dense regions where galaxies could form. Thus, dark matter was the invisible framework that guided the formation of the universe from the chaos of the Big Bang. The role of dark matter extends beyond merely being a scaffold. It is integral to the stability and formation of cosmic structures. Observations of galaxies and galaxy clusters show that visible matter alone cannot account for the observed gravitational effects. Dark matter provides the additional mass needed to explain these phenomena. For instance, the rotational speeds of galaxies do not decrease with distance from the center, as expected if only visible matter were present. This discrepancy is resolved by the presence of dark matter, which exerts a gravitational pull, holding galaxies together. In essence, dark matter acts as a glue that binds the universe's structures, allowing them to form and persist over billions of years. The influence of dark matter is not confined to the formation of galaxies and large-scale structures. It also affects the universe's overall behavior. Dark matter interacts with normal matter through gravity, influencing the distribution and movement of galaxies. This interaction helps scientists map the presence of dark matter by observing the gravitational lensing effect, where light from distant objects is bent by the gravitational pull of dark matter. These observations reveal the invisible parts of the universe, providing insights into its composition and evolution. The study of dark matter also opens doors to understanding other fundamental aspects of the cosmos, such as the nature of gravity and the potential existence of new particles and forces. One of the most compelling pieces of evidence for the Big Bang and the role of dark matter is the cosmic microwave background. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the infant universe just 380,000 years after its birth. This radiation carries information about the early universe's density fluctuations, which were the seeds for the formation of galaxies and clusters. The patterns observed in the CMB support the presence of dark matter, as they align with theoretical models that include dark matter's gravitational effects. The CMB is a crucial tool in cosmology, offering a glimpse into the universe's earliest moments and the fundamental forces at play. One of the most impactful ways to understand how the universe formed from nothing is to learn about the recombination era. This era, occurring approximately 380,000 years after the Big Bang, was when electrons and protons first combined to form neutral hydrogen atoms. Before recombination, the universe was a hot, dense plasma where photons couldn't travel freely due to constant interactions with charged particles. As the universe cooled, these particles combined, allowing photons to travel unimpeded. This transition marks the release of the cosmic microwave background radiation, providing us with a snapshot of the early universe. The CMB is a relic from the Big Bang, carrying imprints of the universe's initial conditions and offering invaluable insights into its origins. The cosmic microwave background is often referred to as the persistent echo of the Big Bang. This faint, uniform radiation fills the entire universe, acting as a cosmic backdrop. Its discovery in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory. The CMB is remarkably uniform, but it contains tiny fluctuations in temperature. These fluctuations, measured by missions like the Cosmic Background Explorer and the Wilkinson Microwave Anisotropy Probe, reveal information about the early universe's density variations. These variations were the seeds from which galaxies and large-scale structures eventually formed. The CMB, therefore, is not just an afterglow but a critical component in understanding the universe's evolution from an initial state of nothingness. In the realm of quantum mechanics, even a perfect vacuum is teeming with temporary changes in energy levels, creating particles and antiparticles that pop in and out of existence. These fluctuations are minute and usually cancel each other out, but they played a crucial role in the early universe. The Big Bang itself can be viewed as a massive quantum fluctuation. According to some theories, such as those involving quantum cosmology, the universe could have spontaneously emerged from a state of absolute nothingness due to these fluctuations. This concept challenges our classical understanding of nothing, suggesting that even in the absence of matter and energy, the potential for creation exists. These quantum fluctuations didn't just initiate the universe. They also shaped its subsequent evolution. The initial tiny fluctuations in the early universe grew under the influence of gravity, leading to the formation of galaxies, stars, and planets. This dance of quantum fluctuations set the stage for the large-scale structures we observe today. The fluctuations left imprints in the cosmic microwave background, providing a detailed map of the universe's primordial density variations. Over billions of years, these variations were amplified, driven by dark matter's gravitational pull, culminating in the cosmic web of galaxies and clusters. This intricate interplay between quantum mechanics and cosmic evolution underscores the profound connection between the minute world of quantum particles and the vast expanse of the universe. Bringing these concepts together, we see a coherent narrative of the universe's formation from nothing. The era of recombination and the release of the cosmic microwave background provide a window into the early universe, revealing the fingerprints of quantum fluctuations. These fluctuations, arising from the seemingly empty void, acted as the seeds for all cosmic structures. The persistent echo of the Big Bang, captured in the CMB, serves as a testament to these early processes. Quantum mechanics, with its counterintuitive principles, offers a framework for understanding how the universe could emerge from a state of absolute nothingness, driven by the dance of quantum fluctuations. This interconnected story highlights the intricate tapestry of forces and phenomena that gave rise to the universe as we know it. The concept of quantum fluctuations plays a crucial role in understanding how the universe could have formed from nothing. These fluctuations are temporary changes in energy that occur spontaneously in the vacuum of space. Even in the absence of matter, in the early universe, these fluctuations were amplified by inflation, a rapid expansion that occurred fractions of a second after the Big Bang. This amplification led to the creation of tiny, uneven distributions of matter and energy, which eventually grew into the large-scale structures we observe today, such as galaxies and clusters. The practical implications of this are profound. It means that the universe's initial conditions, seeded by quantum fluctuations, set the stage for everything that followed. Without these fluctuations, the universe might have remained a uniform, featureless expanse. Cosmic voids are vast, empty spaces between clusters of galaxies, comprising about 80% of the universe's volume. These voids are not truly empty, but they contain far less matter than other regions of space. In the context of the universe's formation, cosmic voids offer a unique perspective on the concept of nothingness. They are regions where the density of matter is exceedingly low, yet they play a significant role in the universe's overall structure. The existence of cosmic voids supports the idea that the universe is a complex and dynamic entity, where even the seemingly empty regions have a part to play in its grand design. These voids help us understand the distribution of matter and the gravitational forces at work on a cosmic scale. Despite their name, cosmic voids are not completely empty. They contain dark matter, sparse gas, and sometimes even galaxies. The presence of dark matter within these voids is particularly intriguing because it does not emit, absorb, or reflect light, making it invisible to traditional detection methods. However, its gravitational effects can be observed. The subtle presence of dark matter in cosmic voids contributes to our understanding of the universe's structure and evolution. Dark matter acts as a scaffold, influencing the formation and distribution of galaxies. This subtle yet significant presence underscores the idea that even in the vast nothingness of cosmic voids, there are essential components that shape the cosmos. The universe's formation from nothing is also evidenced by the persistent traces of matter left behind. These traces can be seen in the cosmic microwave background, the afterglow of the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old, revealing slight fluctuations in temperature that correspond to regions of varying density. These density variations are the fingerprints of the universe's earliest moments, imprinted by quantum fluctuations. As the universe expanded and cooled, these traces of matter coalesced to form stars, galaxies, and other structures. The CMB is a vital tool in cosmology, offering a glimpse into the universe's infancy and the processes that led to its current state. The expansion of the universe is a fundamental aspect of its evolution, directly linked to the concept of nothingness. According to the Big Bang theory, the universe began as an infinitely small, hot, and dense point, which then expanded rapidly. This expansion is still ongoing, driven by a mysterious force known as dark energy. The idea that the universe is expanding into nothing challenges our conventional understanding of space and time. It suggests that the universe creates new space as it expands, rather than expanding into a pre-existing void. This concept is difficult to grasp, but it is supported by observations of distant galaxies moving away from us, indicating that the fabric of space-time itself is stretching. The expansion of the universe from a seemingly nothingness state underscores the dynamic and ever-changing nature of the cosmos. Bringing these subtopics together, we can see a coherent narrative of the universe's formation from nothing. Quantum fluctuations provided the initial seed of matter and energy, which were amplified by cosmic inflation and left persistent traces in the form of the cosmic microwave background. Cosmic voids, though seemingly empty, contain subtle presences of dark matter and sparse gases that contribute to the universe's structure. The ongoing expansion of the universe into nothing highlights the dynamic nature of space-time and the continuous creation of new space. These interconnected concepts illustrate the profound and intricate processes that transformed a state of apparent nothingness into the rich and diverse universe we observe today. The birth of the universe is a fascinating tale that begins with the concept of cosmic nothingness. Before the Big Bang, what we perceive as nothing was an empty space, but rather a quantum vacuum where particles and antiparticles continuously appeared and disappeared. According to quantum mechanics, these fluctuations could have given rise to the Big Bang, a massive event that marked the beginning of time and space as we know it. This theory suggests that the universe emerged from an incredibly dense and hot singularity, expanding rapidly in an event known as inflation. During this brief period, the universe grew exponentially, smoothing out any irregularities and setting the stage for the formation of matter. As the universe expanded and cooled, it reached a critical phase called recombination. This period occurred around 380,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen atoms. This process had a profound impact, allowing photons to travel freely through space for the first time. These photons are now observed as the cosmic microwave background radiation, which provides a snapshot of the universe in its infancy. The CMB is a faint glow that permeates the entire cosmos, offering critical insights into the early universe's conditions. It marks the first light of the universe, illuminating the path from a hot, opaque plasma to a transparent, expanding cosmos. Following recombination, the universe entered a period known as the Dark Ages, a time before stars and galaxies had formed. However, the seeds for cosmic structures had already been sown. Tiny fluctuations in the density of matter, left over from the inflationary period, began to grow under the influence of gravity. Over millions of years, these fluctuations attracted more matter, eventually leading to the formation of the first stars and galaxies. These early stars ignited through nuclear fusion, producing light and heat, and beginning the process of reionization, which made the universe transparent once again. The formation of stars and galaxies marked the end of the cosmic dark ages and the beginning of the structured universe we see today. The formation of galaxies and their subsequent evolution from the initial state of nothingness is a remarkable process. As matter clumped together under gravity, galaxies began to form, often in clusters and superclusters. Dark matter, an invisible and mysterious substance, played a crucial role in this process. It provided the gravitational scaffolding necessary for galaxies to form and hold together. Observations of the large-scale structure of the universe reveal a vast cosmic web, with galaxies and clusters connected by filaments of dark matter. This intricate structure emerged from the initial quantum fluctuations, illustrating how the universe evolved from a seemingly empty vacuum to a richly textured cosmos filled with diverse galactic formations. The universe we observe today can be thought of as a grand cosmic stage, set into motion by the Big Bang and shaped by the interplay of dark matter, gravity, and the fundamental forces of nature. This stage is adorned with countless galaxies, each containing billions of stars, planets, and other celestial objects. The cosmic microwave background radiation provides the backdrop, reminding us of the universe's humble beginnings. The ongoing expansion of the universe continues to shape this stage, driving galaxies apart and influencing the evolution of cosmic structures. The concept of nothingness, once a profound mystery, is now understood to be a fertile ground for the birth and evolution of the universe. Black holes are among the most enigmatic and fascinating objects in the universe, representing regions where matter has been compressed to an extreme degree, creating a gravitational pull so strong that not even light can escape. They are often thought of as the ultimate voids, where the concept of nothingness takes on a new meaning. In the heart of a black hole lies a singularity, a point where density is infinitely high, and the laws of physics, as we know them, cease to function. This singularity can be seen as a counterpart to the concept of nothingness that existed before the Big Bang. While black holes are created from the remnants of massive stars, their intense gravitational fields and the absence of matter within them make them a compelling topic when discussing the universe's formation from nothing. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. This process results in a supernova explosion, leaving behind a dense core that becomes a black hole. Black holes play a crucial role in the evolution of galaxies and the cosmos. They are often found at the centers of galaxies, including our own Milky Way, where they influence the motion of stars and gas. These supermassive black holes can have masses millions to billions of times that of the Sun, and their gravitational pull shapes the dynamics of their host galaxy. The interaction between black holes and their surroundings provides essential clues about the formation and growth of cosmic structures, helping us understand the broader narrative of the universe's evolution from nothingness. The concept of nothingness has been a subject of philosophical debate for centuries. Philosophers have long pondered the nature of existence and the possibility of a state devoid of anything. In the context of cosmology, nothingness is not merely the absence of matter, but a state where space and time themselves do not exist. This notion challenges our everyday experiences and pushes the boundaries of human understanding. Some philosophical perspectives argue that nothingness is an impossible state because the very concept of it implies the potential for something to exist. Others suggest that the universe's emergence from nothingness is a testament to the complexity and depth of reality, where even the absence of things can give rise to everything we observe. Scientific perspectives on nothingness often intersect with philosophical viewpoints, particularly when discussing the universe's origins. In physics, nothingness can be described as a quantum vacuum, where particles and antiparticles constantly appear and disappear. This dynamic vacuum challenges the classical idea of a true void, suggesting that even empty space is teeming with potential activity. This perspective is supported by theories such as quantum field theory and the principles of quantum mechanics, which describe the probabilistic nature of particles and their interactions. The idea that the universe could emerge from such a quantum vacuum aligns with the notion that nothingness is not a static state, but a fertile ground for creation and transformation. The implications of nothingness extend beyond the realm of theoretical physics and cosmology. Understanding the universe's emergence from nothingness can reshape our views on existence, creation, and the nature of reality. It challenges the conventional distinctions between something and nothing, suggesting that the potential for existence is inherent in the very fabric of reality. This realization can have profound philosophical and existential implications, influencing how we perceive our place in the universe and the nature of our existence. Moreover, studying the origins of the universe from nothingness can drive scientific innovation and discovery as we seek to unravel the mysteries of the cosmos and our beginnings. The concept of nothing has evolved significantly over time, reflecting advances in both scientific knowledge and philosophical thought. In ancient times, nothingness was often associated with the absence of all things, a void devoid of matter, energy, and even space. However, as our understanding of the universe deepened, the notion of nothingness became more complex. The advent of quantum mechanics introduced the idea that even in a vacuum, particles and antiparticles spontaneously appear and disappear, suggesting that nothing is not truly empty. This shift in understanding has profound implications for our conception of the universe's origins, highlighting the dynamic and ever-changing nature of what we once considered a static void. As we continue to explore the cosmos, our understanding of nothingness evolved further. The discovery of the expanding universe by Edwin Hubble in the 1920s revolutionized cosmology, suggesting that the universe had a beginning at a point in time when it emerged from a singularity. This led to the development of the Big Bang theory, which posits that the universe began as an incredibly hot, dense point that has been expanding ever since. This theory implied that, before the Big Bang, there was a state of nothingness from which everything emerged. The notion that the universe could arise from a quantum vacuum challenged classical ideas and opened new avenues for understanding the fabric of reality. Revolutionary insights into the nature of nothingness have come from various branches of science, particularly quantum mechanics and cosmology. One key idea is that of quantum fluctuations, which occur even in a perfect vacuum. These fluctuations involve temporary changes in energy levels that create particles and antiparticles, providing a possible mechanism for the universe's emergence from nothing. Additionally, the concept of cosmic inflation, a rapid expansion of the universe immediately following the Big Bang, helps explain how quantum fluctuations could have been stretched to macroscopic scales, seeding the formation of galaxies and large-scale structures. These insights revolutionize our understanding of nothingness, suggesting that it is a fertile ground for the birth of the universe. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided a crucial piece of evidence for the Big Bang theory. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and offers a snapshot of the early cosmos, approximately 380,000 years after its inception. The CMB's uniformity and tiny temperature fluctuations reveal the seeds of cosmic structure, supporting the idea that the universe began from a hot, dense state and expanded over time. This discovery was pivotal in confirming the Big Bang model and furthering our understanding of how the universe could emerge from a state of near nothingness. Perceiving nothing is inherently paradoxical, as the human mind is conditioned to think in terms of presence and absence. The concept of nothingness challenges our cognitive frameworks, forcing us to confront the limits of our understanding. In cosmology, this paradox is evident in the idea that the universe could emerge from a quantum vacuum, a state that is not truly empty, but teeming with potential activity. The paradox lies in reconciling the existence of the universe with the notion of a preceding state of nothingness. Robotic missions and space probes have expanded our knowledge of the universe beyond what can be achieved with telescopes alone. Missions like the Voyager probes, which were launched in the 1970s, have traveled far beyond our solar system, providing valuable data about the outer reaches of the heliosphere and interstellar space. More recent missions, such as the New Horizons probe to Pluto and the James Webb Space Telescope, have continued to push the boundaries of our exploration. Space probes gather detailed information about the planets, moons, and other celestial bodies, helping us understand their compositions, atmospheres, and potential for supporting life. This data is essential for piecing together the broader picture of the universe's evolution from a state of nothingness. Supercomputing and simulations play a critical role in modern cosmology, allowing scientists to model complex processes and phenomena that are difficult or impossible to observe directly. By using powerful computers, researchers can simulate the evolution of the universe from the Big Bang to the present day, incorporating various physical laws and cosmic parameters. These simulations help in understanding how structures like galaxies and black holes formed and evolved over time. They also enable scientists to test different theories about the universe's origins and predict future observations. The results from these simulations provide a virtual laboratory for exploring scenarios that are beyond the reach of current observational technology. The James Webb Space Telescope represents a significant advancement in our ability to observe the universe. Launched in December 2021, JWST is designed to observe in the infrared spectrum, allowing it to see through dust clouds and capture light from the earliest galaxies formed after the Big Bang. Its advanced instrumentation and large mirror enable it to gather unprecedented detail about distant cosmic objects. JWST observations are expected to provide new insights into the formation of stars, galaxies, and planetary systems, further illuminating the processes that shape the universe from its earliest moments. This telescope is a key tool in revolutionizing our understanding of cosmic history and the origins of the universe. The second Lagrange point is a crucial location for space observatories like the JWST. Positioned about 1.5 million kilometers from Earth, L2 provides a stable environment with minimal interference from Earth's heat and light. This location allows telescopes to have an uninterrupted view of space, essential for observing distant and faint cosmic objects. The journey to L2 involves precise calculations and maneuvers to ensure that the spacecraft reaches and remains in this stable orbit. By positioning observatories at L2, scientists can maximize their ability to collect data and perform observations, contributing to our understanding of the universe's formation and evolution. The concept of time is integral to understanding the notion of nothing and the universe's formation. In classical physics, time is a linear progression from past to future, a constant backdrop against which events occur. However, in the context of the universe's beginning, time itself is thought to have originated with the Big Bang. Before this event, conventional concepts of time and space did not exist, meaning the universe emerged from a state where time, as we understand it, was absent. This idea challenges our perception of nothingness, suggesting it is not just the absence of matter and energy, but also the absence of time. The emergence of the universe from this timeless state marks the beginning of temporal and spatial dimensions. Modern physics has significantly evolved our understanding of time. In general relativity, time is not separate from space, but is part of a four-dimensional space-time fabric. The presence of mass and energy warps this fabric, affecting the passage of time, a phenomenon known as time dilation. This means time can pass at different rates depending on the gravitational field and relative motion. Quantum mechanics adds another layer of complexity, introducing the concept of quantum fluctuations, where particles and energy appear and disappear spontaneously, affecting time at microscopic scales. These theories suggest that time is not a fixed, absolute entity, but a dynamic, relative aspect of the universe. This modern understanding of time provides a framework for comprehending how the universe could emerge from a state of near nothingness, where time itself is fluid and interconnected with the fabric of space. While diving deep into the concept of nothing, time dilation also comes forward. Time dilation is a phenomenon predicted by Einstein's theory of general relativity, which describes how time can be stretched or compressed depending on the strength of a gravitational field. In regions of strong gravitational fields, such as near a black hole, time passes more slowly compared to areas with weaker gravitational fields. This effect is known as gravitational time dilation. For instance, if you were to observe a clock near a massive object, you would see it tick slower compared to a clock far away from that object. This concept is crucial for understanding the nature of time in the universe, particularly in the context of extreme environments like the early universe or the vicinity of massive cosmic structures. Robotic missions and space probes have expanded our knowledge of the universe beyond what can be achieved with telescopes alone. Missions like the Voyager probes, which were launched in the 1970s, have traveled far beyond our solar system, providing valuable data about the outer reaches of the heliosphere and interstellar space. More recent missions, such as the New Horizons probe to Pluto and the James Webb Space Telescope, have continued to push the boundaries of our exploration. Space probes gather detailed information about the planets, moons, and other celestial bodies, helping us understand their compositions, atmospheres, and potential for supporting life. This data is essential for piecing together the broader picture of the universe's evolution from a state of nothingness. Supercomputing and simulations play a critical role in modern cosmology, allowing scientists to model complex processes and phenomena that are difficult or impossible to observe directly. By using powerful computers, researchers can simulate the evolution of the universe from the Big Bang to the present day, incorporating various physical laws and cosmic parameters. These simulations help in understanding how structures like galaxies and black holes formed and evolved over time. They also enable scientists to test different theories about the universe's origins and predict future observations. The results from these simulations provide a virtual laboratory for exploring scenarios that are beyond the reach of current observational technology. The James Webb Space Telescope represents a significant advancement in our ability to observe the universe. Launched in December 2021, JWST is designed to observe in the infrared spectrum, allowing it to see through dust clouds and capture light from the earliest galaxies formed after the Big Bang. Its advanced instrumentation and large mirror enable it to gather unprecedented detail about distant cosmic objects. JWST observations are expected to provide new insights into the formation of stars, galaxies, and planetary systems, further illuminating the processes that shape the universe from its earliest moments. This telescope is a key tool in revolutionizing our understanding of cosmic history and the origins of the universe. The second Lagrange point is a crucial location for space observatories like the JWST. Positioned about 1.5 million kilometers from Earth, L2 provides a stable environment with minimal interference from Earth's heat and light. This location allows telescopes to have an uninterrupted view of space, essential for observing distant and faint cosmic objects. The journey to L2 involves precise calculations and maneuvers to ensure that the spacecraft reaches and remains in this stable orbit. By positioning observatories at L2, scientists can maximize their ability to collect data and perform observations, contributing to our understanding of the universe's formation and evolution. The concept of time is integral to understanding the notion of nothing and the universe's formation. In classical physics, time is a linear progression from past to future, a constant backdrop against which events occur. However, in the context of the universe's beginning, time itself is thought to have originated with the Big Bang. Before this event, conventional concepts of time and space did not exist, meaning the universe emerged from a state where time, as we understand it, was absent. This idea challenges our perception of nothingness, suggesting it is not just the absence of matter and energy, but also the absence of time. The emergence of the universe from this timeless state marks the beginning of temporal and spatial dimensions. Modern physics has significantly evolved our understanding of time. In general relativity, time is not separate from space, but is part of a four-dimensional space-time fabric. The presence of mass and energy warps this fabric, affecting the passage of time, a phenomenon known as time dilation. This means time can pass at different rates depending on the gravitational field and relative motion. Quantum mechanics adds another layer of complexity, introducing the concept of quantum fluctuations, where particles and energy appear and disappear spontaneously, affecting time at microscopic scales. These theories suggest that time is not a fixed, absolute entity, but a dynamic, relative aspect of the universe. This modern understanding of time provides a framework for comprehending how the universe could emerge from a state of near nothingness, where time itself is fluid and interconnected with the fabric of space. While diving deep into the concept of nothing, time dilation also comes forward. Time dilation is a phenomenon predicted by Einstein's theory of general relativity, which describes how time can be stretched or compressed depending on the strength of a gravitational field. In regions of strong gravitational fields, such as near a black hole, time passes more slowly compared to areas with weaker gravitational fields. This effect is known as gravitational time dilation. For instance, if you were to observe a clock near a massive object, you would see it tick slower compared to a clock far away from that object. This concept is crucial for understanding the nature of time in the universe, particularly in the context of extreme environments like the early universe or the vicinity of massive cosmic structures. The relativity of time is a core principle of both special and general relativity. In special relativity, time is relative to the observer's state of motion. For someone traveling at speeds close to the speed of light, time would pass more slowly compared to someone at rest. This effect, known as time dilation, means that time is not absolute but depends on the observer's velocity. General relativity extends this concept by showing that time is also affected by gravity. These relativistic effects mean that time can vary across different regions of the universe, influenced by both the observer's movement and the presence of massive objects. Gravitational time dilation specifically refers to the slowing down of time in strong gravitational fields. This phenomenon has been confirmed through various experiments and observations. For example, precise measurements of time using atomic clocks on Earth's surface and in orbit show slight differences due to Earth's gravitational field. Gravitational time dilation is particularly significant in extreme environments, such as near black holes or neutron stars. Understanding this concept helps explain how time can behave differently across the universe and provides insights into the early moments of the universe. When gravitational forces were extraordinarily strong, cosmic expansion is a phenomenon where the universe has been growing since the Big Bang, with galaxies moving away from each other over time. This expansion affects our perception of time and space. As the universe expands, it stretches the fabric of space-time, influencing how time is experienced across different regions. The expansion rate, driven by dark energy, leads to a dynamic and evolving universe. This continual expansion means that the universe is constantly changing, and time, as we experience it, is intertwined with the expanding space-time fabric. Understanding cosmic expansion is essential for comprehending the large-scale structure of the universe and its evolution from a state of near nothingness. Quantum mechanics introduces a different perspective on time compared to classical physics. In the quantum realm, particles exist in states of superposition, where they can be in multiple states simultaneously. This inherent uncertainty affects our understanding of time at microscopic scales. Unlike the deterministic view of time in classical physics, quantum mechanics suggests that time is probabilistic and influenced by quantum fluctuations. These fluctuations played a crucial role in the early universe, potentially giving rise to the Big Bang. From a quantum vacuum, quantum mechanics challenges our classical notions of time and introduces new complexities in understanding how the universe emerged from nothingness. Wormholes, theoretical passages through space-time, are solutions to the equations of general relativity proposed by Einstein and physicist Nathan Rosen, hence sometimes called Einstein-Rosen bridges. These hypothetical structures could, in principle, connect distant points in space-time, allowing for instantaneous travel across vast distances or even different times. If wormholes exist, they might contain closed time-like curves, which are paths in space-time that loop back on themselves, theoretically allowing for time travel. This suggests that one could travel back to an earlier point in time, raising fascinating possibilities and significant challenges for our understanding of causality and the fabric of reality. The concept of time travel, especially through wormholes, introduces several paradoxes that challenge our understanding of logic and causality. One well-known example is the grandfather paradox, where a time traveler goes back in time and prevents their grandfather from meeting their grandmother, thereby preventing the traveler's own birth. This creates a logical inconsistency. If the traveler was never born, how could they travel back in time to prevent their birth? Another paradox is the bootstrap paradox, where an object or piece of information sent back in time becomes the very thing that triggers its own existence in the future, creating a loop with no clear origin. These paradoxes highlight the potential contradictions and complexities involved in time travel, questioning the consistency of the timeline and the nature of free will. Resolving these paradoxes requires new theoretical frameworks or interpretations of physics that can accommodate such scenarios without violating fundamental principles. In the quest to understand the universe, we often grapple with distinguishing intrinsic elements of reality from human constructs. Intrinsic elements are those that exist independently of human perception, such as the laws of physics, fundamental particles, and space-time itself. These elements are the building blocks of the universe, governing its behavior and evolution from the Big Bang to the present day. On the other hand, human constructs are concepts and frameworks we create to interpret and understand these intrinsic elements. Examples include mathematical models, theories, and the concept of nothingness itself. While human constructs are essential for making sense of the universe, they are ultimately shaped by our cognitive limitations and cultural context. Understanding the difference between intrinsic elements and human constructs helps clarify the nature of the universe and our place within it. Emergent properties are phenomena that arise from the interactions of simpler elements, but are not predictable from those elements alone. In the context of physics, many complex behaviors and structures in the universe are emergent properties. For example, temperature is an emergent property of the kinetic energy of particles in a substance. Similarly, the structure of galaxies, stars, and planets are emergent properties of gravitational interactions and nuclear forces. The universe itself can be seen as an emergent property of fundamental particles and forces interacting over time. This concept is crucial in understanding how the universe evolved from a state of near nothingness, simple initial conditions with basic particles and forces, into the complex and structured cosmos we observe today. Emergent properties highlight the richness and complexity that can arise from simple beginnings. The Novikov self-consistency principle is a theoretical framework developed to address the paradoxes associated with time travel. Proposed by Russian physicist Igor Novikov, this principle posits that any events that occur as a result of time travel must be self-consistent, meaning they cannot create paradoxes. In other words, if time travel to the past is possible, the actions of the time traveler must be such that they fit seamlessly into the existing timeline, preventing any contradictions. For example, in the case of the grandfather paradox, the principle suggests that any attempt to prevent one's grandfather from meeting their grandmother would fail due to some self-consistent mechanism, thus preserving the traveler's existence. This principle provides a way to reconcile time travel with the laws of physics by ensuring that causality remains intact. When combined, these theories suggest that inflation might not only produce our universe, but could also explain its intricate structure and the consistency of the laws of physics we observe today. The mysteries of the universe, from the quantum vacuum to the emergence of space-time, and the intriguing possibilities of wormholes and time travel, challenge our understanding of reality. These profound concepts highlight the intricate interplay of physics, philosophy, and human curiosity in unraveling the secrets of existence. As we explore emergent properties, paradoxes, and the very nature of nothingness, we are reminded of the boundless complexity and beauty of the cosmos. For more captivating explorations into the wonders of the universe, do subscribe to Cosmic Lens and stay tuned for more such fascinating documentaries.